Hello, it's Keith here, and this is lesson 70 of the platform-specific series of my 6502 assembly programming tutorials. Today we're looking at the Atari Lynx, and what we're going to be doing is we're going to be taking the previous min-tile example and we're going to be adding music to it, and that music is interrupt driven. It's timed to the VBlank interrupt, so we're going to be learning how to set up interrupts on the Atari Lynx. So that's what we're going to be taking a peek at today. Now, like most 6502 based systems, we have a set of interrupt vectors. A vector is simply a 16-bit memory address, and the address at these vectors is executed during the various kinds of interrupt. So it's going to be the IRQ interrupt that we want to take control of today at memory address FFFE and FFFF, 2 bytes of course. So that's what we're going to need to change, but the slightly tricky thing, only very slightly, is that by default is a ROM based address, so that area is ROM. However, it's only slightly tricky because the Atari Lynx is very kind and allows us to actually page very small sections of the address space individually into RAM. So that's what we're going to do. Let's go over to our code. Let's take a peek. So this is the example code we're going to be using today. Sometimes you would see a set of vectors at the bottom of our ROM cartridge, but not today because we're going to do it all in RAM. So we've got our setup here at the start. But when it comes to actually setting up our interrupt handler, the first thing we're going to do is we're going to control the paging. And this is done with the memory mapped port at FFF9. There's a memory mapped register here basically, and the bits all can correspond to different parts of the address space. So these bottom 4 bits are the ones we're looking at here, and you can see we've set bit 3 to 1, and that basically changes that area of the ROM into RAM. The V marker there is the vectors. This is this address range here, which is of course the one that we need to change for our IRQ. We don't need the other ones. They aren't going to do any harm to us today. But we could, if we wanted, page out the other memory mapped hardware, the video hardware and things like that. We don't want to, so we're going to leave those well alone today. But we do have the granularity to actually page those in and out independently, which is very nice to have. So that set up the memory for our interrupt vector. So now the next job is to move the address of our interrupt handler, which is imaginatively named interrupt handler, and we just write the address of that, 16 bits, to the corresponding address, the IRQ address just there. Okay, so that's set up our interrupt handling code, but there aren't actually any interrupts which are going to fire yet. We now need to tell the hardware to actually cause the VBlank interrupt. We do that with port FD09, so we're loading in the current value at that memory mapped register there, and then we are just setting the top bit there, and this will enable the interrupt, which is a VBlank interrupt. So we're just storing the new value there, and that has now told the hardware to generate interrupts. The final job is to tell the 6502 to accept the maskable interrupts, so we're just clearing the interrupt mask there, and that will enable interrupts. So now the interrupts are enabled, they are being caused, and we have the code in place to actually receive them. And that code we can just see right now. We've got the typical basic interrupt handler here for the 6502. The 6502 automatically pushes the flags register, so we don't have a PHP-PLLP combination here. We don't need it. It's done for us. The RTI command will actually pull the flags and return, so we need to use that RTI because, as I say, the interrupt handler is doing that push of the flags, so that's the corresponding return. And then all we're doing here is we are backing up the accumulator and the X and Y registers here. We're storing them down here. And then the ChibiTracks music software, which is my music player. This uses all of those registers X, Y, and A, but it also uses some entries in the 0 page. These 16-bit pairs here that are defined as HL, D, E, B, C, and IX. If you don't know what they are, those are mimicking Z80 registers. I use pairs of 0 page entries to mimic Z80 registers because this, like most of my code, is ported from the Z80. But you don't need to know what these mean. They don't really mean anything as such. They're just pairs of 0 page entries that I've defined labels to. So I'm using my push pair and pull pair macros that pull and push a 16-bit pair to back up and restore those 0 page entries there. Okay, now that's how we actually update the music. How do we play the music? Well, playing the music with ChibiTracks is very straightforward. We do need a little bit of code to actually handle the playing, of course. The main entry is the ChibiTracks assembly file here, but that uses some shared routines, the tweener and fraction 16. These are for calculating in-between notes. There's 16 possible in-between notes between each sort of defined note. I thought I might use those again later on, so I've defined them as separate ASM files just in case I make changes and improvements later. We also have Chibi Sound Pro. Now this is a bit more important in some ways because while these are effectively all parts of the same block of code, this is actually platform specific, so there's a different version of Chibi Sound Pro for each piece of hardware, and it's abstracting the functionality of the hardware into a common way. The ChibiTracks is common to all 6502 systems, and there's a port for it for the Z80 and 68000 as well, which is virtually identical. But Chibi Sound Pro, this is the driver that handles the actual job of making this system's music hardware play sound in a common way. So that's what we've got there. And then finally, we've got the song file. This is the file we played today. So that binary file will play on any system, even it's 68,000, even though that's a big Endian system and today's is a little Endian. The player handles all of that kind of thing, and the Chibi Sound Pro sound driver does its best job to make the music sound similar on all of the systems within reason. So that's the software. Getting it to play is very straightforward. First, we run Chibi Sound Pro init. That initializes the platform-specific driver as required. We then load the address of the song we want to play, song 1 in this case. We load that to song base, so that's loading the 16-bit address. We then run ChibiTracks start song. Now, we do have one extra option here. We are overriding the song speed. Now, by default, the song that we're playing today has a song speed of 5. However, I've changed it to 6. This effectively slows it down. The reason I'm doing this is the way I've set up the Atari Lynx today is in 60 Hertz mode, but the song was written for a 50 Hertz system, so it will play a little bit fast, and so I can override that just by changing the play speed. That's what we've done there. So that's the option there, and then that's all we need to do to get the song ready to play. All we need to do to actually update the music is simply run this command here, ChibiTracks play, in this case in the interrupt handler, but you could use a very crude loop if you were just playing music on a static title screen as well. It doesn't really matter how you actually update the music, just so long as you do, otherwise the same note will play forever. Anyway, that's how we get the music playing. There are a few options we do need to discuss though. Now, ChibiTracks and Chibi Sound Pro need a little bit of memory. In total, it's about 128 bytes. A little bit less on some systems, depending on how Chibi Sound Pro works, because each system's different. But it's always less than 128 bytes, so it's safe to assume that. So we're defining a memory address for that RAM here. We're then defining some pointers within that area for the various variables that the ChibiTracks software needs. So we're just sort of basically just tagging those onto the end of the Chibi Sound RAM itself. Might as well keep them all together. We don't actually need to change these very often. As I say, I'm overriding the speed today, but generally you'll just want to leave those the same unless you're doing something clever like sharing a set of instruments between two songs, which you could do if you wanted to make the songs smaller. You could have one instrument set and 5 different songs playing with the same instruments. Why not? Anyway, that's all a bit advanced for today. There are a couple of options we can enable or disable depending on our needs and our memory availability. Allow relocation allows the binary music files to be loaded into any destination memory address. If you disable this, the player will be a little bit smaller and slightly faster. However, you would have to export the binary music file from the ChibiTracks Windows software for the specific memory address you're planning to load into. If you were only using a single system, wouldn't be too bad, but because I do multi-platform programming, the same memory address often isn't available on every system. Some systems have video memory all over the place, some systems have ROM all over the place, so being able to load to any destination memory address is worth the extra cost in program code in the final program. But if you didn't need that, you could disable allow relocation. Allow speed change, we discussed today, we're changing the speed from 5 to 6. If you don't need that capability, you can disable allow speed change. That will make the player a little bit smaller and a little bit faster, and it would make more of a difference than allow relocation, because allow speed change is changing the code for every single time the music's updated, so it would make a more significant speed difference, but not very much again. But if you disable this, what you need to do is you need to enable, when you export the binary file, pre-multiplied speed, because otherwise without that speed change option, without that multiplying the speed into the binary file, then the music plays too fast, as you just heard. And if you don't enable that multiplication when you export the binary file from the Windows ChibiTracks Pro software, then you do need to allow speed change on playback. Otherwise, the speed isn't being represented in the played back music. So it is an option you've got there. But anyway, that's really all there is to ChibiTracks, ChibiTracks Pro, my music software. It's free open source. You can go to the website, you can download today's example code. You can download the Windows ChibiTracks software, which is it's a .NET application that's open source as well. So you can have a play with it and do whatever you want with it. Hopefully you can get some use out of it. And I don't think you can, but as I always say, just for completeness, if you manage to use it in any commercial project, you're welcome to do so. You don't even need to give me credit, because I'm hoping you can get some kind of use out of it. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.